Okay, so welcome back to lecture once again, guys. Now, in this lecture, I'm going to talk about a Spark architecture and in very depth. So there are a multiple component which falls inside a Spark, and one by one, I'll try to break down each and every component. That's a part number one. Now, before that, so we have to understand that why we are going to use a Spark and where we are going to use a Spark. So see guys, a Spark is almost 100x faster than a conventional data processing engine. Technically, Spark is a data processing framework or a data processing engine. So whenever you are dealing with a huge volume of the data in a distributed system, this is the place where a Spark framework comes into a picture and it is going to make your life easy. That's a part number one. Spark supports basically different programming languages. Spark supports Java, Spark supports Scala, Spark supports R programming language, Spark supports even Python programming language, which is called as PySpark, which we are going to explore. So doesn't matter from which like a programming background you are coming from. So obviously you will be able to use Spark. Not just that. So inside a Spark, you will be able to find out a core Spark module. You will be able to find out a Spark SQL module. You will be able to find out a Spark streaming module. You will be able to find out a Spark machine learning module as well. So it doesn't matter whether you are working as a data scientist, you are working as a big data engineer, or maybe you are just a SQL guy, or maybe you are trying to do a real-time data streaming, you will end up using a Spark. This is how powerful Spark is. And if it is that powerful, so obviously it must be having a sort of architecture, right? To process a data set at the end of the day. And I believe we all should understand and we all should know about that architecture. And that is something which I am going to discuss in this entire lecture. So let me share my screen and let's start talking about it. Plus, you will be able to understand more and more as you will go in depth of the practical, or you will start writing a code, you will start processing a data. But yeah, it's one of the fastest framework, one of the fastest framework available on this planet, so that you will be able to process a huge amount of data in a distributed mode in a easiest possible way. So let me write down over here, guys, that Spark architecture. Yeah. Now, so whenever we talk about a Spark architecture, so the very first component which will come in your mind is called as RDD. So what is the full form of this RDD? So full form of RDD is resilient distributed data set. Now, what is a meaning of this resilient? What is a meaning of a distributed, and what is a meaning of a data set? One by one, let's try to understand. Because whenever you are going to process a data inside a Spark, this is a basic data structure Spark is going to use, and it is going to process your data set. So this is the teeny tiny smallest component that you are supposed to understand before understanding a full Spark architecture. So let's try to understand this. Okay, so first of all, what is the meaning of a resilient, by the way, right? What do we understand with this particular meaning called as resilient? So resilient in English, right? So resilient in English, it simply means that a kind of an entity or anyone, so who will be able to recover quickly from a setback or from a difficulties, and that is something called as resilient. So we'll try to understand that why people have given this name as a resilient, right? So why it will be able to, or Spark will be able to recover quickly from any kind of a setback, or how, why and how. So it will be able to recover from a setback quickly. Plus distributed means, so data is available all across a different kind of a system, or different node, you can say, or workers, and it will be able to process those data set in a fastest possible way. So here, to understand this resiliency, to understand this distribution, so we have to understand our properties one by one. So see guys, the property of RDD, if I'm going to talk about, so obviously the very first property is what? It is resilient. So it will be able to come back from a setback or from any kind of a disturbance. Technically, it means that it is a fault tolerance that we are talking about. So fault tolerance simply means that let's suppose if I'm trying to perform some operation, for example, so let's suppose I'm trying to process a data. So I'm trying to perform the data read operation, and then maybe on top of that, I'm trying to perform some sort of a filter operation. Then on top of this data, I'm trying to perform some sort of a mapping operation. Then on top of that, I'm trying to perform some sort of maybe count operation, and then I'm trying to maybe print this entire data after processing this entire things, means reading, then filtering, then mapping, then counting, and then I'm trying to print this data. Now there is a possibility that when it is trying to process this entire pipeline, so it may break down, right? It may break down in between. So maybe system will crash, maybe the entire code is going to crash. So till map code is working fine, but when it comes to count, so it is going to crash, maybe the entire system is going to crash. So when it will try to resubmit a job, or it will try to re-execute a job, so it will be able to come back from a setback automatically. So it will be able to execute, right? So it will be able to start the execution. So it will try to start the execution from a beginning automatically. And this is where this resiliency factors comes into a picture, and how it will be able to achieve it, by the way, how it will be able to achieve a fault tolerance. So basically, whenever you are going to submit a job, for example, this is one of the job I'm talking about, right? So this is one of the job which I'm talking about. So whenever I am going to submit this kind of a job, so internally it is going to create this entire flow that I have created over here. And this entire flow is called as lineage, Lineage, lineage. So this is something called as lineage graph. So whenever you are going to submit any kind of a job, means program obviously, so it is going to create a lineage graph in a very first place. It will not start executing a job one by one. No, not at all. So first of all, it is going to create a lineage graph, and based on that, right? So based on this lineage graph, it is going to create the complete logical plan. It is going to create a complete physical plan, and then it is going to execute your job. So we'll try to come to this logical plan and a physical plan in a later stage. But first of all, try to understand this resiliency property and how it will be able to achieve it. So how it will be able to achieve it? By creating a lineage graph, right? Lineage graph. Now, what is a lineage graph? Nothing but a kind of a logical plan that, okay, I will be doing this, then 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 I will be doing this, right? And it will keep tracking of it that, okay, so this is done, okay, this is done, okay, this is done, okay, this is not done. So it has broken somewhere in between. So it will try to re-execute a job once again, because it has already created a lineage graph, right? It has already created a lineage graph. So it will try to take a help from a lineage graph, and it's called as basically fault tolerance, right? It will be able to achieve that fault tolerance. Now, so this is one of the property that you will be able to find out. Now, the second property, and the most important property I would say, is called as lazy evaluation. Lazy evaluation. So in general, so if we'll talk about any other framework, so what it does, whenever I'm trying to perform, or I'm going to write a code like read a data, right? So it will read a data. Doesn't matter that what we are doing with that data, like a reading. So there is a possibility, right? There is a possibility that I'm trying to read a data, but after that, I'm not doing any kind of a process, right? So in general, I will end up exhausting my resources. In general, I will end up exhausting my network IO. In general, I will end up exhausting my compute, and then even a main memory, right? If I'm loading a data and if I'm not doing it. Plus, let's suppose I have loaded a data, but certain columns or maybe certain records are not required. Maybe I have to apply the filter beforehand before reading a data. So even in that way, I will be able to save a lot of compute power, a lot of network IO, and lot of main memory. So other framework are not handling in that way. But in case of Spark, so like I said, whenever you will try to read a data, so first of all, it will try to create a data structure, which is technically a RDD, and property of RDD is one is resilient, right? By which it will be able to achieve the fault tolerance by creating a lineage graph. The second property is lazy evaluation. Lazy evaluation means what? So let's suppose I'm reading a data, right? But what I will do if I'm just reading a data, so if I'm not doing any kind of things with respect to that data, it's like I'm not doing anything, right? So, and then I'm trying to perform a filter operation, but what after that, right? So basically I'm trying to read a data, I'm trying to filter a data, I'm trying to perform a mapping operation with respect to this data, I'm trying to perform a count operation with respect to this particular data, right? So basically this map operation is technically called as transformation operation. So we are doing a data transformation by mapping a data, by filtering a data. We are just trying to perform a transformation operation. So in case of a Spark, there are two kind of operation exist. So one is basically transformation operation. For example, a map operation, filter operation, reduce by key operation, or maybe a flat map kind of a operation, right? So this is basically called as transformation operation. Now, whenever you are trying to perform a transformation operation, so a Spark will never go ahead and execute it because you are not looking for any kind of a final outcome, right? You are not looking for any final kind of a outcome. Now, so when it is going to execute a job, so simply means that when I'm trying to call a filter operation, when I'm going to call a map operation, it is trying to create a lineage. Only it is trying to create a lineage graph, nothing more than that, right? But it is not actually executing your data. Means it is not actually reading your data. It is not actually filtering out anything out of the data. It is not actually trying to do any kind of a mapping operation with respect to the data, because these are the transformation operation. So it will try to execute it. So when you are going to call any kind of a action on top of this, and what are the action operation? For example, I'm trying to perform a count operation. I'm trying to perform a collect operation. I'm trying to perform maybe some kind of a saved as a text file kind of operation, right? So these are basically a action. Action means the operation, so which is going to give you the output, right? So this is called as lazy evaluation. Lazy evaluation simply by definition simply means that unless and until I am not looking for a final output, right? So unless and until I'm not looking for a final output, I am not going to execute it. Very simple. So it will not execute this one. It will not execute this one. It will not execute this one unless and until you are not calling this one. It will be a part of lineage, but it is not going to execute it, because execution simply means that you are trying to occupy a resources. You are trying to occupy my network IO. You are trying to occupy my RAM, which is main memory. You are trying to occupy my compute power, right? A CPU, my GPU, you are trying to occupy. So this is how a Spark again try to optimize the entire resource planning, right? So RDD is technically a resilient. Resilient means fault tolerant. So even if like it is just going to crash, it's completely fine. With the help of lineage graph, it will be able to recover and it will be able to execute the job. RDDs are technically a lazy execution like a data type. So which simply means that it is not going to execute it in a transformation. So unless and until you are not looking for the final output, technically that is called as action operation. Yeah. So once you are going to basically call the action operation, it is going to execute it, as simple as that. Yeah. So hope all of you are able to understand the lazy evaluation. The third property of RDD is basically distributed. Resilient, second word is basically distributed data set, right? So distributed. Now, what is the meaning of this distributed, by the way? Yeah. So let's suppose I have a cluster, right? I have a cluster and I have a data into a different node. So basically it is going to create the RDD. So maybe I have a data here, 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 here. So technically RDD is going to combine maybe each and everything as per the need, and then it is going to process it. Simple. So from the different system, right? So maybe from system 1, maybe from system 2. So it will try to bring the data and then it will try to process a data. So RDD is basically a distributed. And again, so distributed means I will be able to get a huge amount of a computation without giving a load on one single machine. So I will be able to execute process a data set, right? So this is where this distributed comes into a picture. Now, so RDDs are technically immutable. So immutable simply means that the transformation that you have created over here, the lineage graph that you have created over here, you can't change it once you have created, right? You can't change it once it has been created. So maybe you can create a new, but you can't change it. So this is the reason it's basically called as immutable. Immutable. So RDD is technically a immutable entity, means once that lineage graph has been created, once that RDD has been created, you will not be able to mutate it at all. Yeah, you will not be able to mutate it at all. So, okay, this is the property of a RDD. Now, let's suppose I'm trying to process this data, right? I'm trying to perform this operation. So how this operation, let's suppose I have written a code. Yeah, operation means what? So operation simply means that I will write the code to read the data, then filter, then apply, then count, and then maybe try to print it or maybe try to save it. Yeah, this is the meaning of it, right? So let's suppose I'm trying to perform these operations. So how end-to-end Spark is going to perform this entire operation? So let me explain you in a very, very detailed manner now, because the core component we are able to understand. Okay, so let's try to understand the final overview that how a Spark is going to execute. So let's suppose I'm writing a code. Yeah, so I have written a code. Code for what? So code for the above process. So first of all, read a data, then apply the filter, some sort of filter on top of the data, then map the data, then count, and then maybe try to print it or maybe try to save it. So first of all, I will try to write a code. Now, what will happen with the code? So I'm going to submit this code into a driver program or into a driver, or it's something called as Spark session. So a Spark session is an entry point for any one of us for the very first time whenever we are going to execute a job. So here we are going to submit it to the driver. Driver is nothing but a Spark session, right? So I have written a code. I'm going to submit to a driver program. Now what it will do internally? So internally, right? Internally, it is going to create a logical plan. It is going to create a physical plan for my entire job. Let's try to understand, and then one by one, I am going to break it down that what is technically a meaning of a logical plan, what is technically a meaning of a physical plan, by the way. So here, it will go inside the Spark session, so means a driver program, and then over here, right? Then over here, so it will try to call a catalyst optimizer. So CATALYST, catalyst optimizer. Catalyst optimizer it is going to call. Now what this catalyst optimizer is going to perform? So it is going to create a logical plan. Yeah, it is going to create a logical plan, you can say. And then it is going to call, so then it is going to call a tungsten optimizer. Tungsten, or you can say CodeGen optimizer. So which is going to basically generate a bytecode, which is going to generate a bytecode of a physical plan. So this is technically called as physical plan. Yeah. And after this, so once this will be done, so it is going to create something called as direct acyclic graph. So DAG scheduler, it is going to invoke. And then once this DAG scheduler will be invoked, so this is going to invoke basically something called as task scheduler. Now once this will be done, then it is going to call the executor, right? And inside that, it is going to basically execute the final job, or you can say it is going to call something like a resource manager executor, right? So basically resource manager is going to allocate our resources, and then eventually executor is going to execute it, where internally it is going to run the entire task. It is going to manage the entire block. Now one by one, let's try to connect each and everything and then try to understand each and everything. Yeah. So I have written a code that's cool. That's completely fine for me. Now, so once I'm going to submit a job, once I'm going to submit a code, so obviously a Spark session will come into a picture, and it will try to instantiate a Spark session saying that okay, so I have to execute this particular job. Yeah, I have to execute this particular job. Now, once it is going to say that I have to execute this particular job, then this logical optimizer, which is nothing but called as catalyst optimizer or catalyst rule based step or catalyst optimizer, comes into a picture, and which is going to, right? So which is going to optimize your entire code base or your entire plan in a logical level, right? So basically logical level, it is going to optimize each and everything. For example, right? For example, so if you have written somewhere like so how logical is going to execute it? So let's suppose if somewhere I have written 1 plus 2, so automatically it will try to replace it with 3, right? Automatically it will try to replace it with the 3. Or maybe so it will try to apply a filter automatically. So let's suppose if you have written something called as greater than 100 or lesser than this one, so it will try to apply those filter automatically, or it will try to filter the entire expression. For example, if I have written, I'm just giving you example, couple of example that how it is going to execute it. So let's suppose if I have written where a is equals to 5 and true, right? True. So internally what it will do? So it will try to convert this entire lengthy logic to where a is equals to 5. Simple. So into a simple logic. So this is how this logical plan comes into a picture. So it will run through the entire code, and technically it will try to convert your entire logic that you have written in an optimized way. And that's the reason. So it's called as optimizer. So our name is catalyst optimizer. So it is going to optimize your code in a logical manner. Then once it is going to optimize your code into a logical manner, then there will be a physical plan comes into a picture. Now, what is the meaning of this physical plan, by the way? So this physical plan is nothing but, so here the entire code, right? The entire code. So what this tungsten optimizer or code gen optimizer is going to do? So this tungsten optimizer or code gen optimizer is going to turn the entire operators into a optimized Java bytecode, so that my code is going to be very, very fast. Let's suppose if I have written code into a PySpark or maybe into R, maybe into a Java. So at the end of the day, it is going to convert your entire code into a optimized Java bytecode. Yeah, it is going to perform, or it is going to optimize this entire code into a Java bytecode. So now if my code is available into a bytecode, so obviously on a low level, it will be able to execute it in a fastest possible manner, right? And this is where the power of again Spark comes into a picture. So one from the logical and one from this particular physical, and again RDD, the basic component that we have already discussed about, right? So here it is going to use a project. So there was a optimization project called as Tungsten project. So here Spark is using a Tungsten project so that it will be able to optimize a heap memory. It will be able to do a better garbage collection, by the way, right? So better garbage collection. It will be able to build even a better cache friendly data layout, right? And eventually it is trying to convert your entire code into a bytecode. So obviously your code will be very, very fast. So this is something that it is going to perform. This is something that is going to perform. Now, once this will be done, right? Once this will be done, then what it is going to do? So till this step, right? Till this step, you can say, till this particular step, you can say that, okay, so it is going to keep, or it is going to happen inside the RDD, right? It is going to happen inside the RDD. For example, so if I'm going to submit the code, so here it is going to read a data. Let's suppose from a distributed system, it is able to read a data and it is able to create a RDD. Now inside that, so obviously it will try to do a logical optimization. It is going to do a physical optimization. So now I have a bytecode which is available to me. Yeah, bytecode which is available to me. Now, so once my bytecode will be available, right? Once my bytecode will be available. So here what it will do. So let's suppose we have to finally process the data, but immediately it will not go for a data processing. What it will do, it will try to create something called as DAG scheduler. Yeah, DAG scheduler. So let's suppose I have a job, right? So I have a job. I'm going to submit a job. Now, what a DAG is going to do internally. So let's try to understand a DAG a little bit before going into this particular flow. So how DAG is and what is basically a DAG. So if I'll talk about a full form of a DAG, so it's called as directed acyclic graph. So directed acyclic graph. Now, what is the meaning of directed, by the way? So basically a meaning of directed is execution flow in one direction, right? In one direction, not in two direction. So from input to output, one direction. So this is basically a meaning of a directed. Now, what is the meaning of acyclic? No cycle, means no loop. And graph simply means that there will be a multiple node which is trying to represent a different kind of a job. So this is technically a full form of a DAG. Now, where this DAG comes into a picture, so as per my previous diagram, so once our physical plan will be ready, right, then DAG comes into a picture. Now, what we have done till physical plan, so we are pretty much sure that we have converted our entire code into a byte code. This is what we have done till this stage, right? This is what we have done till this particular stage. And then DAG is coming into a picture. This directed, like a directed acyclic graph coming into a picture. This DAG scheduler technically coming into a picture. Once we are done with the physical plan. And we now know that, okay, so what we are doing till a physical plan, converting our code into a byte code. So very low level optimization we are trying to perform over here. Okay, so here, after this RDD, which I'm trying to represent, so this DAG will come into a picture. DAG, directed acyclic graph, will come into a picture. And what this directed acyclic graph is going to perform, right? What this directed acyclic graph is technically going to perform. So let me explain you that what it is going to perform inside this entire Spark component one by one. So here, let's suppose we are trying to process our data as per the above requirement. And for that, we have submitted the code. So we are trying to perform these operations, right? And for that, we have written the code. And finally, my code is available into a physical plan. Means code is available as a byte code. Now, the entire Spark is going to listen to a DAG. Whatever way DAG is going to create the execution, right? It is going to execute it. So maybe like some data we have to execute it before, some data we have to execute it after, some data or some code we have to do it maybe at some point of a time once both of this data, both of the previous data will be executed. So this is where this directed acyclic graph comes into a picture, and it says that okay, so I'm going to take a physical plan, means I'm going to take this output of this byte code, right? Output of this byte code. And then I'm going to split it into a different small stages that, okay, first I will execute this, then I will execute this, then I will execute this, then I will execute this. So it is going to split it into a small stages, and it is going to arrange it, right? It is going to arrange it, saying that okay, so this will be executed first, this will be executed second, this will be executed third, this will be executed in a fourth place. This is what this entire DAG operation is going to perform. So simple, right? Simple. So if DAG is saying that okay, so you and you will be executed together, it will be executed together, right? If it is saying that you and you will be executed together, it will be executed together. If it is going to say that you will be executed alone, right? And maybe you will be executed here as well. So it is going to execute in this particular order, and this job will be scheduled as per the DAG. Now this DAG scheduler, DAG scheduler, DAG scheduler is going to arrange your entire job, and then this will go inside your cluster manager at the end of the day. Cluster manager. So if you are running your job into your laptop, so in that case it is going to be standalone. If it is a single machine, it is going to be standalone, or it is going to use Yarn, it is going to use a Mesos. If you are using a Hadoop infrastructure, then obviously Yarn, it is going to use it as a cluster manager, and cluster manager will be responsible for, right? Responsible for allocating you the resources as per the plan that you are going to submit. And how I'm submitting a plan? With the help of DAG. And finally, it is going to do the execution, right? Execution, and then you will be able to get what? So you will be able to get technically a output. So this is a flow Spark is going to follow. This is the complete flow Spark is going to follow. So first of all, it is going to build the RDD, right? Resilient distributed data set. So which is going to be the building block, I would say, for any kind of a operation that you are going to perform inside Spark. Then it is going to perform a DAG, but before performing a DAG, it is going to basically call a catalyst optimizer, which is going to optimize it logically. And then it is going to call a tungsten or code gen, you can say. So which is going to convert your entire code into a byte code. And then it is going to create a DAG. So it is going to make an arrangement that, okay, so which one will go first, which one will go second, which one will go third. So in a one direction, in a unidirection. So it is going to create the entire graph. And then finally, it is going to submit it inside the node manager, or you can say a cluster manager. Sorry. So cluster manager, and then it will go for the execution. So once it is going to get the resources. So this is how, right? So this is how this entire process is going to happen, guys. Yeah. This is how entire process is going to happen. And finally, you all will be able to get your output. So this is the complete holistic overview of a Spark architecture. And these are the components you will keep on listening again and again and again. And when I'm going to execute a Spark job, I'll try to show you even all of these components inside a Spark UI. It's possible. It's possible to track each and every stage and what kind of a DAG it is trying to create, what kind of a RDD it has created, and how it is trying to, get resources, how it is trying to execute it, how it is going to give me the output. If job is failing in between, then how this resiliency comes into a picture, which is going to help me out in terms of achieving a fault tolerance. Each and everything you will be able to see it inside a Spark UI, which I'm going to show you, So while taking a practical lecture. So till then, hope all of you have enjoyed this entire lecture. All of you are able to understand this Spark architecture. With that, thank you so much, everyone. Take care and see you again in my upcoming lectures.